Okay. Good morning. Oh, that was loud. All right, so the exam results came back. The course-wide average was 75, which I'm very happy about. That's a very good number. Very pleased to see the performance with an average of 75. That's wonderful stuff. The cutoffs for this exam are 90 or above for an A, 80 or above but below 90 for B, 65 for C, and 50 for a D. The scores should be on WebAssign. If not, it should be on there soon. Okay? I randomly checked a few gradebooks just now, and look like most TAs have put in the exam scores. So check your WebAssign gradebook to see your exam score. You'll get your exam back next week, maybe Tuesday, maybe Thursday. Okay? Okay, these cutoffs are just for this exam only. Remember, we don't have any preset cutoffs for course grade. So again, these are just for the exam. It doesn't mean that at the end of the semester, these are the numbers that we'll go with. We will probably adjust each one of these. But if you get A's on every exam, chances are you're in good shape to get an A. If you got below a D on every exam, chances are you're not doing so well. Okay? If you're concerned about your grade, it's just one exam. You have two more and the final exam to catch up. So don't freak out right now. If you did well, keep up the good work. You have two more exams and the final. There are plenty of chances to screw up. So what I'm saying is don't get too cocky, and also don't panic. Okay, today we're going to look at section 7.3. And the topic is on integrating with trig substitutions. There are many, many integrals that we can calculate using U substitution or integration by parts. But you run into a lot of integrals, like this one, for example. If we were to integrate 1 over radical 1 minus x squared dx, if I were to use a regular substitution, I would choose 1 minus x squared to be u. Right? It's a very obvious choice. And that would tell me du equal to minus 2x dx. So when I do the substitution, this stuff downstairs is simply u to the power of 1/2. That's not a big deal. But then we run into a very big problem here with dx. I need x dx to form du, but I'm missing that x here. I can't find that x anywhere to make a du. That means I cannot use that method here to integrate that. There's simply no way to proceed any further. This is something that we cannot handle with substitution. So this is one of the typical things that trig substitution comes in handy. So let me show you how trig substitution works. The first thing we're going to do here is to form a triangle. With these three sides. The first side is this stuff in the denominator. The second side is this first number here, but with a square root. And the third side is this thing here under square root, so simply x. Okay, so you grab this radical thing in the denominator that becomes one side, and then the other sides come from these two parts. Whatever this number is under square root, whatever this is under square root. Then you form a right triangle with those three sides. So here's my theta, and there's my right angle. Now you got to decide which one of these goes to, well, you got to decide where do they go. You have three sides, three quantities. Which one goes where? Let me show you how this works. Notice if you look at this number, 1 minus x squared here, this implies that 1 is always bigger than x squared. Because the side has to be a real number, so we can't have a negative number under a radical. So this implies 1 is bigger than x squared. So 1 must be bigger than x. Okay? And this is some square root of the difference of the two. So this is telling you that 1 goes to the hypotenuse. And then you got 2 left here. The 2 can basically go anywhere you want them to go. But what we want to do is to put the radical here, and then the x over here. And I'll talk more about other cases where what goes where. So this is the first thing we want to do. Get a triangle with these three sides. Decide which one goes to the hypotenuse, and then take the other two sides. So here again is the hypotenuse first. And then adjacent next. And then once you got these two, the remaining side only has one thing to go. The next step here, this is kind of a slightly complicated process when you first look at it. I'm going to go through the process, and then we'll come back and look at everything again. The next thing here is to relate theta to x in the simplest way possible. So for example, I can say sine of theta is equal to x over 1, right? Or I can say cosine of theta is equal to adjacent over hypotenuse. Or I can say tangent of theta is the opposite over the adjacent. You always want to choose the simplest one possible. And this is no contest here. This is the simplest one, right? Sine of theta. So here's the key of the substitution. From here, we see that x is equal to sine of theta. So in the original integral, we're going to replace this x here with sine of theta. But we have to do the same thing with dx. Just like any regular substitution, you replace the thing you call u and then du, right? Same thing here. We have to find dx. So dx here is cosine of theta, d theta. So these guys go into here. I'm just rewriting the things we need. So now you see downstairs, well, we can calculate this thing on the side here. Right? 1 minus x squared under a radical is 1 minus sine squared under a radical. And what's this under a radical? Cosine squared, right? And we end up getting cosine, right? We take the positive root of the square root. So that stuff in the denominator now turns into cosine. And don't forget dx. That's a very important part of the whole thing here. Right? Dx becomes cosine of theta d theta. Oh, theta, sorry. So cosine theta, they cancel. We end up getting d theta. And what's the integral of d theta? Theta and c. Good, wonderful. And so you see, we turned this integral that we couldn't handle into something ridiculously simple, which we can integrate right away. Very important, don't stop right here. We don't want the answer in terms of theta. It's just like when you do u integration, u substitution, we don't stop with the answer in u. We go back to x. Same thing here. We substituted theta in, we integrated in theta. Now we got to go back to x. And how can I do that? How do I go back to x? Right. I can look at this one here, for example. Or I could go back to my triangle. But this is probably the simplest way to do it. X is equal to sine theta. So how would you write theta? Good. Or inverse sine of x, right? So therefore, this turns into the inverse sine of x plus some constant c. And you might have recognized in the beginning that this is the derivative of inverse sine that I think we did one example a while back using an inverse sine. So you might remember that being the derivative. So now you see another way to come to that conclusion that this is the derivative of inverse sine. Okay, so let me walk through the process again. When you see this kind of thing, start with a triangle. The three sides come from whatever the expression that is, the number square rooted, x by itself. And then you decide which one is the largest one. Then you grab the next one to put in adjacent, and you continue with that. and then integrating theta. Let's try another example. Well, try a few more, not just another one. So a definite integration this time. So we're integrating the same kind of thing here. It is radical of some square thing going on. A regular substitution doesn't do the job again. If you let this be u, your dx is still missing an x term to get your du. So we'll retrace exactly the same steps. We want a triangle with these three sides. Radical 4 minus x squared, and then square root of 4, and then square root of x squared. Okay, so this time, which one is the hypotenuse? 2, because 4 minus x squared implies that this square must be bigger than that square, right? And this has to be something less than the difference of those two. And you can tell that by looking at this expression. That if it's a subtraction, the first thing that comes under a square root goes to hypotenuse. That must be the biggest term. So it goes here. Now we have two sides to choose to put onto adjacent. Always choose the one that has a constant involved. Our choices down for this step here were this or that. You always want to choose the one that has a constant. This one doesn't. That does. And then once you made that choice, the last one goes to the opposite. Questions so far? We okay? Okay, now find the simplest way to relate x to theta. What do you think? Yeah, sine again, right? Opposite hypotenuse. So that means x is equal to 2 sine theta. Just like last time, we need dx. We also want to take care of the integration limits. The integration limits used to refer to x. We're going to go into theta now, so they have to refer to theta. So actually, let's take care of this guy first. And then we'll do the limits. and we get 2 and cosine theta. Okay, so we got this taken care of. We got dx taken care of. 0 and 2, that's the next thing to do. The old upper limit was at 2. X is equal to 2. Now we need to know what theta that refers to. All right, so if you look at this one here, if x is equal to, this is x. If x is equal to 2, theta is equal to inverse sine of 1. So what angle has a sine of 1? Pi over 2, excellent. Then x is equal to 0. That means theta is the inverse sine of 0, right? What angle has a sine of 0? 0, yep. Now we took care of everything. We know what to do with that in terms of theta. We know what to do with that in terms of theta. We took care of the integration limits. We shove everything into the integral and see what we get. Let's see. Radical 4 minus x squared turns into 2 cosine theta. And dx turns into 2 cosine theta. So what do we get here? We get 0, pi over 2, 4 cosine theta squared. Remember how to integrate this from Monday? Yeah, half angle, right? Remember? And this turns into what? Plus or minus? Plus is right. Okay, I'll show you an easy way to remember in a little bit once we finish this up. So that's a 2, which I'll take outside. And then what's left here is simple, very easy to do. We get a theta from the 1, and then this is 1/2 sine of 2 theta. So we get pi over 2 plus 1/2 sine of 2 times pi over 2 minus 0 plus 1/2 sine of 0 and 3 of these are 0, 0, right? 0, nothing, nothing. So pi over 2 times 2 is a pi. Questions? Yes. Because I don't need to. Why? His question is, how come I didn't go back into x? Because I changed the integration limits to refer to theta. So I just simply complete the integral in theta. Now, you could leave them in terms of x, but then you got to go back to x. And then you may run into a problem. You may have to do some inverse trig thing that we did anyway when you go back to x. So might as well get them up front and finish the whole thing and not change back and forth. All right, so let me show you an easy way to remember the half-angle identity, which goes with which. So what you need to remember is that cosine of 0 is equal to 1, right? So notice when I put 0 into here, I get 1 plus cosine of 0 over 2, 1 plus 1 over 2, which is 1. And I know that sine of 0 is 0. So you can see if I put in a 0 into here, I should get 0. So you just need to remember that the form of these two things. The plus and minus, you just remember which goes with which. Cosine of 0 is 1. In order to get 1, this has to be a plus, right? So that's the easy way to remember. You just remember the form, and the plus and minus come from cosine and sine by themselves. Let's do more substitution. X cubed over the square root of x squared plus 4. Anytime you see some kind of radical involved, that's always a very, very good indication that we're doing trig substitution. And just like before, we're going to come up with a triangle with 3 sides. Which 3 sides? What are they? Right, this guy right here, and then, yep, and then 2, good, right? X square of x under a root is x, 4 under a root is a 2. I want you to think carefully which one is the hypotenuse. Yeah, why? Right, it's an addition of 2 things, right? So it's got to be bigger than these 2 squared individually. It's an addition of the 2 other sides under a square root. And you remember the Pythagorean theorem, hypotenuse squared is equal to square of this plus square of that. And that's exactly why this thing goes to the hypotenuse. Can't spell that. A-D-J, yeah, adjacent. Adjective, good way to remember. Okay, remember the rule? Which one goes to adjacent? Right. If you can choose to put a constant, put a constant to adjacent. Okay, the reason is because we choose the remaining sides, the one with the constant involved. The remaining sides were x and 2. 2 is the one with the constant involved. And then x has nowhere to go except the opposite. Questions so far? Are we okay with how we got this triangle? Yep. Good? Yes?
Why do you always choose the side that's constant to be
Good question. It actually, strictly speaking, doesn't matter. But if we choose the constant side to be the adjacent side, then we only need to use 3 trig substitutions as opposed to all 6. So it keeps things simple. Okay? That's just for convenience here. But like I said, strictly speaking, doesn't really matter. What's next step? Simplest way to relate x and theta, right? So looking at a triangle, we're going to work with the opposite and the adjacent. What trig function works with those two? Tangent. Very good. So there we go. This means x is equal to 2 tangent theta. So that takes care of these x's. What's dx? What's dx? I need to hear more. Good. D theta. Okay, so we took care of x, we took care of dx. Let's take care of these other guys. What do we get here? We get 4 tangent square plus 4 under a root. 4 times the quantity of tangent square plus 1 under a root. So this is a 2. 4 comes out of a root, becomes a 2. What does tangent square theta plus 1 turn into? Good. And under a root, secant comes out. And then x cubed. Well, that's simple. That's simply 8 tangent cubed, right? So the 2 cubed is 8. Tangent cubed is tangent cubed. Same process as before, different substitution, but that's not a big deal. You make a triangle, use the triangle, replace every x, everything there, and then go to theta. Let's see, our new integral turns into x cubed on the top, so that's 8 cube of tangent theta. Downstairs is 2 secant. And dx is 2 secant squared d theta. right? So let's see, 2 and 2 cancel. Here's an 8. Let's bring it out of the integral. This cancels one of those factors. So we get 8 times the integral of the cube of tangent theta and the secant theta. Okay, we dealt with this thing last time. Remember the rule? Yeah, think about what u should be. If u is tangent, then du is secant squared. I don't have secant squared. So u must be secant, right? And derivative of secant is secant tangent. So I need to save one factor of secant, tangent, sorry. So now I want to go to secant world. And tangent squared is, how is that related to secant? Secant squared minus 1 plus 1 minus? Who says minus? Who says plus? Minus, yes. Okay, so here's an easy way to remember. We know that, right? We know that. That's simply something you know. Divide through by cosine squared. So we get 1 plus sine squared over cosine squared is what? Tangent squared. What's 1 over cosine squared? Secant squared, right? So there you go. If you know this one here, dividing by cosine gives you the other one. So you see, tangent must be secant squared minus 1. So here we let u be secant. So we get u squared minus 1 du. So what do we get? We get 8 over 3 u cubed minus 8u plus some other constant. We got 2 layers of substitution here, right? We went to theta, then we went to u. Now we got to go back 1 layer at a time. So here we get secant cubed, 8 secant by itself plus c. Now back to x. Use your triangle to go back to x. Or actually we have, yeah, that's the way to do it. So from the triangle, secant is what? Hypotenuse over adjacent, right? Because cosine is adjacent over hypotenuse, secant is the other way around. So it's a radical x squared plus 4 over 2. Okay, then you toss that in there and you are done. that secant is this, so secant cubed is that cubed, minus 8, that stuff, plus a constant. And you can simplify that further, but that's not really the point. The point is that getting here. Okay, so you see, often you need layers of substitution. First go to theta, and possibly another u substitution. Questions? All right, let's do one more. One over x squared times radical x squared minus 16. Right away, you look at the radical part. Use that to form triangle. So that's one side of the triangle. The remaining two sides are what? Right, x and square root of 16. See that? Okay, this time hypotenuse, right? The guy leading under the radical, that's your hypotenuse. If they are added together, then the whole thing is hypotenuse. Adjacent. We actually have two things involving constant. Choose the simpler of the two when that happens. When you have a choice, when you got two remaining constant sides, choose the simpler of the two. And that's always just a constant by itself. So let's see, we want adjacent here. So the opposite, oops, no. I wrote here, hypotenuse is x. So who's left? Oh, this guy's left. And by the way, always verify the Pythagorean identity here. Square of this plus the square of that equal to that. Squared, right? So 16 plus x squared minus 16 is x squared, which is that squared. And now we relate x to theta. Two simplest sides are adjacent and the hypotenuse. So what do you think? Which trig function can relate those two? Cosine can do that, so can secant. We'll try both. Cosine is the adjacent over hypotenuse, and the secant is the thing upside down. They're the same thing, really, because if you look at this left expression, you get what the right expression tells you. So even if you had chosen cosine, we end up going to secant anyway, right? Okay, now we got x. Now we do dx. for secant theta tangent theta, d theta, x squared, 16 secant theta squared, and radicals x squared minus 16. If you plug this into here, you'll find out it turns into 4 tangent theta. Once again, using the second of the Pythagorean identity we used earlier to get this thing. Now, every part that we had to get rid of is now in terms of x. Shove all those in. And hopefully we get something we can integrate. Let's do downstairs first. First we see x squared. That's 16 secant squared. And then we see radical x squared minus 16. That's 4 tangent. Upstairs we have a 1 times dx. And dx is equal to, where's my dx? There it is, 4 secant tangent. D theta. Four over 16 is a 1 over 4 that I'll take out. Tangent, tangent cancel. Secant cancels one of these. Oh, there's another 4, so that's 16. Thank you. There we go. And that's a cosine, right? 1 over 16, cosine. So integral of cosine, positive, negative? Positive, good. Plus some constant. Are we done? No, what's left? Right, back to x. So back to x. From the triangle, my sine of theta is the opposite over hypotenuse. So here's my opposite. My hypotenuse is x. So that goes in here for that. Now are we done? Yep, we are done. Okay? All right, so the theme is you got to get a triangle right. Once you get a triangle right, this is relatively straightforward. Okay? All right, that's it. See you Friday.